This video is going to be, yes. So this video is going to be on um, the Insigne protocol and the Muka M for Mike, Q from Molasses, K for Kilo, O for Oscar, uh, um, uh, magnetic enzyme kernel, kernel, for partite, but for bipolar, Endianess. Oh, for tripolar Endianess. forStaless runtime execution. What does this mean? So we have Insiggy, N for November, F for Sarah, I for Indigo, G for Gold, I for India, I for India. We have the magnetic memory kernel model. We're now building a kernel. The kernel is the system that manages the drivers and it's a computer program that does with the actual base interface. So the kernel drivers for the USB for any kind of external ports. We're gonna be using the protocol, L for Lima, I for Indigo, B for Bravo, P for porridge, O for Oscar, L for Lima, Y for Yankee, C for Charlie, Alpha Lima, Alpha Lima. The protocol is the world's first polyglot system, and the protocol is uh, uh, the protocol is the world's first polyglot system. So what does the kernel do? The kernel is a program that manages hardware devices and peripherals, hardware peripherals via the driver. All bindings are drivers. Not all drivers are bound. All squares are seamlessly bidirectional F-function interfaces. They work in bidirectional, and then kind of basically squares have a transmitter and receiver. They have a bidirectional via the user and the author, the consumer and the user. So the consumer and the customer. Think of it as services. And you can have a square, a triple force that you can have a rectangle, and you're gonna have control over the driver. The driver gives you more final control over the two perpendicular sides that connect and adapt, and two other sides the shoulder that for the adapter pattern using to build via the broker. So I'll now get to my demonstration of the thing I'm going to achieve here, but my camera will be off, and I'll show you how this works. So we are dealing with, before I start, we're dealing with magnetic systems in the kernel, which is basically magnetic enzyme model, which is basically an invariant of the system we're building. What we show send into the system. Now, the magnetic enzyme model is basically create, again, destroy, build, break, renew, and repair, and eliminating or eliminating one of these operations ensure stability in the ecosystem but magnetism. So look at this as a quantum computer, and the tripolar Endianess model is for left shift, right shift, and left Endianess via a self-balancing tree of called an AVA3, and the right Endianess via a right Endianess tree balance. So you have a tripolar tree that will use to detect whether a system can have data or not, and the driver can boot it or not, load it into or not. What does it matter? How does it work? And how does it matter? It works because endians is basically bipartite. Endians can be left shift endians, starting from the left to read the numbers, the binary numbers, or right shift, right endians. So you're gonna write endians because you're gonna have two kind of endians operations. We have a three kind of endians operations in the model because we are trying to model three colorable graph. So trying to detect kind of arbitrary configuration and kind of instruction set of Cisco and Risco, of the instruction of the codec of the byte. For example, if you have 0110, the calculator 0, if you have the number 0110, you're talking about 0110. If you have 0110, you have decimal 6. But decimal 6 can be represented in other way, basically right Endian notation. Writing this will be uh, 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 serial number 6. So you have a number of basically some so 0, 1, 2. So 6 is a number here, but you're gonna have 0, 1, 2, 6. If you have a number that goes into flows overflows into into a parallel system or 6, you have more numbers. The more numbers you can come, but the endiness you can detect what the number is. And a tripolar endiness can recover this. A tripolar endiness can be used for ever recovery, and that's why for biparallel system, for kind of the two-standard version of binary system, if you think of a one, if you think of a Hamming code as a tripolar system. So it's not an Hamming code per se, but it's basically it is a Hamming code actually, but it's basically on representing information in based on native measurement of native architecture. And that's what I'm saying. So you're gonna have a tripartite system that will color coded numbers, and the color coded numbers are gonna have an endianness of for stateless runtime execution of SIGI. What does this mean practically? Practically, this means by having a tripartite three-color red, green, and blue as colors of three-color coding, green meaning that the system is good to go to the number. The green means a green number in a rotating tree can balance numbers based on parity elimination. Now, parity elimination is if I give you a 1, you give me a 0, and we decide what is basically consensual, yes or no. Yes or no. Yes or no. In a three axis, you have a consensus of 3 times 3, which is 9, but the three are yes, no, yes, no, yes, no. And this enforces consent. So you have yes, yes, no. If you have a yes, you're talking about 1. So the matrix of this will be yes, yes, no. Yes, no will be 1, 0, 0. Yes, no, no will be yes. Okay, so you have 1, no, 1, 0, 0, 1, 1, 0, 1, 0, 1, representing the parity matrix. Now, the parity matrix is basically a matrix that determines the color is blue, and is the corrective code of the water in the matrix based on a shuffle. And this matrix determines what can be corrected and what should be corrected in what is stateless. Now, the goal is to have a magnetic memory model. Use this matrix of 1, 1, 1. I mean, 1, 0, 0 as a row, 1, 1, 0 as another row, and 1, 0, 1 as another row, standing for yes and no, to determine kind of the parity of the tripolar state of a color codec. More formally, I'm trying to take this parity matrix to resolve a Hamming code, Hamming code as a Hamming code. I can use a Hamming code to recover outliers based on magnetic results, principles. Now, the self-balancing tree have an R open. So if you go to github.com/R open, you can see how this works. I made a video on Rift Open, R open, because R open uses a bridge to do so. And you can compile DLLs and systems of DLLs and dynamic libraries on other systems without an overhead in the system, because the system has no indexes. I'll show you 2 demonstrations today of ropen and what happens when you use ropen and the runtime execution of SIGI. Let me show you now. So here with my computer, this is the directory of ropen here. Rift ropen. So ropen is on github.com / obnexus obnexus of Oscar, B for Bravo, I for Indigo, N for November, E for Echo, X for X-ray, U for Umbrella, S for Sarah, /r_open. Now, I'll show you how to use this. So you're gonna have the files here. You're gonna have the README documentation. But as you can see, there's two compiled binaries here when you use the makefile. So basically, it's a sparse duplex of encoding 2 to 1. But the red band, basically the red black AVL pruning prunes out systems of non-latency, and you can use it for the magnetic system. So the main system basically takes magnets into account to polarize them. As I mentioned, basically, if a magnet is a lattice order is used to, because you have a lattice, basically an order theory or group theory of lattice, used to model a sparse duplex of encoding. So you're gonna have two physical bytes, one logical byte, and this is polarity A, normal nibbles, and B, use conjugate nibbles, and the nibbles are represent the nibbles of bytes. Nibbles are is it 2 bytes is a nibble? Yes, this is nibble is two bits is a 1 byte, 2 bits representation is a nibble. So you got a bit, you got a two bits, and you got a triple. So you got like a triplet, and the triplets are sparse duplets. You can anything nibble to determine how to have or two physical bytes equals no, two physical bytes are nibble, and three physical bytes three physical basically not really basically R represents a single file that encodes any ELF binary into a 2 to 1 duplex stream, A or B polarity, by pruning out negative noise of the red-black tree and a half log in registering and 1/4 time for log space tape. So this is R open virtually. So this is the one project I'm working on. Two physical bytes are usually to map to one logical. Two physical bytes are used to map to one local. Well, two physical bytes are used to map to one logical byte, and the polarity determines the kind of normal nibbles. Um, a normal which are two bits of information, and polarity is conjugate nibbles. So conjugate nibble will be the opposite ending to determine the kind of information on codec. But it's a 3 to 1 mapping for the codec system in this kind of new version I'm working on. The epsilon padding ensures that there's an odd length of nibbles in odd length of inserted inside the O length, so you can keep information while it's being computed. So this is what happened in R open, and this is basically the magnetic principle that I'm trying to enforce as a magnetic system. So it's not preserved as a stale state. Staleless execution is a runtime procedure, which we'll show you. This is how you compile it. GCC the shared O2 ropen the DLL, that's WL, that's output input lift open the A. So you have a share library and a dynamic library, and you can use it to open any kind of files, any kind of codec system, any kind of codec system. So you're gonna have the system open codec system, and using ropen it's a library that can work on Windows, Mac, or Linux based on the kernel implementation or the kernel magic. The kernel magic basically allows you to open three kind of systems: Windows, Mac, and Linux, so you can run any kind of a codec on the system. So you can use this one here, command run a. So this order probability in one sentence closer in half and log times. I'm busy. Hello, I'm busy. 1 second. 1 second. So like I'm saying to you, the system is tripartite, meaning it's tripolar, so you can have three kind of coloring, but this is a two kind of coloring system here. But this is our rule. So you can open any file based on a codec system. Doesn't matter the kind of file you open, you just it stands the codec and you can use it to build a library, such as system of libraries. So let me get a one image. This is basically the riff.png image. This is basically the OBNFS image. And if I take this command and I run it here, /r open. R open here, exe, rift open the you can open this here. And the product of A is used to do the codec. We can have the product of system. So you're going to have the inverse codec or the product of B, but product of B. You can have the product of B. As you can see, the codec is reversed, but this is a small image. So, this is when it puts an image, this is our open. So it puts an image to show you how to open an image. This code is more or less similar. Let me find a different image on my computer. One second, let me find a different image on my computer. Found it. Okay. So I've got an image. It's got uh, me, me, and the me is here. I found the image now. Let's go. So you go here, and you go here. The image is basically called me.png. So I do ls me. I can open it dot slash rift open, rift image, priority, open me. And this is coded for the system, priority A, B. And now I can open it, I can type this into Explorer, and it should give me the image itself. So let me just find the keyboard. Shift, sorry, the operator is Explorer. So the Explorer is here. So this is the operator method. So it should work. I'll open slash me JPG variety B. Basically, oh no, it's basically priority B is gone. Just exe dot. Basically, it's not opening a bad, so I just use this policy A. Normally, basically, it does work, but it doesn't work. I don't know what it's doing. But you get the codec system, and let me try to find the instruction manual. How I did it. So you're gonna have obviously the encoding image here, and you're gonna have the output, but the output a hex string of these 4 bytes. You're gonna have the bytes determine the constructor. Okay, it's not working. I don't think it's working. The duplex encoding, pruning of stage 4 bytes. But you're gonna have the R open with the PNGA. So you're gonna open the image here. So basically, the image is going to open, but any kind of encoding this system will open. But I can't open explorer.me, open.me.jpg. But this is the image here. Let's try to use WSL to do it because this. Oh yes, does to run the shell. So basically, this program run the shell is basically going to open the 2 images here. So you get run the shell, shell script, cat run the shell, can't run the shell, you have our open image, priority beacon, GCC, GCC function position, shared, yeah, the open main, open C, dot slash dot slash run a shell, shell, line, dot slash, uh, you can open this image here. Oh, this is codec. So this is just a more codec of the same image, but this this image is soft. So the coding of the image. If I use IOStream to write, if I write this image first, byte to byte, this is a extension version of the image, and this is encoding of behind the image. So this encode of the image itself. The image is basically a decimal representation of the image. What else now? But it does work. I just don't know how to open. Let me just use pipe open. Pipe explode. I can't put it on an image. I don't know what it's not working open up, but it's not working until I use IO stream. IO dot stream. The read bytes. Read bytes. And then the part of I'm trying to debug this. I don't know how so basically. Read bytes. Read bytes 512. On stream bundles. Read bytes. Read bytes. 512. 521. 512. And it would be dot slash read name. Right. Yeah, that's what's up. Yeah, uh, yeah, oh, yeah, yeah. So basically, it's not working antenna, but it does work when you have an image viewer. They can on terminal, but as I'm claiming here, and these are basically a system that use the library to do so. And that's the first project stop. The second goal of the project is to use relay verify. So you're gonna have me have this here to relay the MOOC OS. You're gonna have the MOOC OS. You're gonna have Infomike from Kilo or something. I'm gonna have the relay GPS system. I'm gonna show the GPS system as it works right now, but this works. So if I go here, if I go here and I run, this file, if I run dot slash, you can go build dots or just reverse dot and build on rules. You can type this in the SIGI GPS reform. This is a repository in SIGI GPS relay, and it's a relay system that replaces states of due based on the magnetic one. So the magnetic kernel is important. The magnetic kernel shows that the replay system, basically the magnetic system operates at runtime, and that's insane. So basically, I'm gonna now go on a low walk and show you that it does work. I'm offline, so it will not work. So if I run in SIGI GPS relay serve, I get a signal. I think it's here. Oh, the map is missing. Basically, I'm here on the map. I'm blue. And it's a browser GPS service, but I'm not gonna move. So I have to connect to the internet first. Let me turn on my camera and go to the internet because my camera. I'm just turn off here. I'm just turn off here, and I'll show you because I need to connect to the internet. 1 second, guys. My push is kind of low too. But I'll show you me walking around, connect to the internet, and working. Okay, so as I'm saying to you, I've been working in here, and I'll show you how this works. So this would be system model. So basically, you found me here. I'm right here, and if I click here, I'll walk down the road and show that I'm moving. I'm moving. So for me, yeah, this is me here, and because I'm here in the move, I can't. There's there's a fence here. You can see here because it's me, and this is basically this is a magnetic system. As you can see, the library is built go build dot built executable, and we have the linkable identity holder to magnetic system. So this is a library that's magnetic. So if I now walk here, given my IP address, I'm going to. So I'm gonna walk now and show that it can work for me. Mhm. So I'm walking here. I can see I'm moving, but you can't see me move. Oh, it's now going slow. But as I'm moving, the camera's getting bigger. So let me just try to. So as I'm moving right now, my location is moving, and you can see the map is moving, and I'm moving because I'm with my map, and because I'm going somewhere, it's moving. So it's basically tracking me in real time magnetically. Doesn't matter where I go, I'm not pressing the keys anymore. It's moving myself to where I'm moving. And now we're here. Now we're here in the computer room. Yeah. So now I'm here in the computer room. Yes. And I'm here and you can see that I've moved a lot, basically. As you can see, I moved quite a bit. So, I moved quite a bit from here to here. I don't know how where I am no more. But I'm here and showing me that I'm here now. Okay. I can print them out if I do not print them out. This is basically system bus. So it shows me I've moved here and I've changed directions. I've been moving here. So now on the computer, I'm showing me here. And now on the computer, but it's not showing me the, because it's magnetic. There's no compile time logic here. It's just a Go binary has been built, and that's the executable binary here has been built. And this is linked to not even linked to the executable magnetic library because there's no reason to link to the new one. But the Go file is just tracking me in real time. So you got a space-time fingerprint, which is literally tracking me in real time as a security measure. I'm gonna have here and now, there and then, and when or where. But you're gonna have based on the food delivery system, the drifter. So you're gonna be moving away. You're gonna be moving away because I'm moving away of the system here. I'm moving away from the structures around me. So now I'm zooming in. Now I'm gonna shut it down. I'm gonna shut it down, clear it, refresh it, and we run it, and we run it. So now I should be here. So now I'm here, but I'm here. Basically, I'm the blue dot. So my intelligence is changed and my intelligence is safe. So it's basically auto-correcting my location based on where I am. And you can see I'm here, and it's 5 kilometers accuracy. So literally up to 5 kilometers, and 5,000 meters accurate. And this is what I'm saying. It's literally instantaneous because it's magnetic. It's instantaneous. So you go now stop this now. So I'm now gonna go back here. Now my face here. Now I'm gonna be going back this way. So it should update the same thing, based on how I'm touching it. So it should be updating in the same way. Okay. I don't care about the doctors. No. I don't care about them. So now I'm going here. I'm up here. Now I'm here. The system here. Here I am. The water like in the kind of like the peanuts of the garden. So in regards to the garden, show you the garden. There's nothing in the laundry here, really. Look, there's nothing in the whole that. But I'm here and it's tracking me in real time, and you can't see anybody here. It's not allowed. So you're gonna be tracking. So I'm tracking. I'm going to the garden and it's not moving anything because it doesn't need to move. But when I get to the garden, it should be able to move. So right now I'm in the garden. I'm going to the garden and there's a chair down there. But I'm saying to you, I'm still going to the garden as to go complete this journey. So let's go. Why not work here? and and that's where it came from. See, I moved. So basically, basically, this to prove, because there's no library that's been read from. There's no DLL. This one. It's just basically the runtime's been updated because the system is magnetic. It knows it will send magnetic principles. It's not just it's no compiler and background. It's not a system. It's magnetic. So it's the runtime update because there's some kind of polar magnetism in the system, and the GPS basically allows me to move freely because it's updating my position as I'm holding the laptop. It's a magnetic compiler system. So here is compile, and here is magnetic, and it allows me to move freely in the world. Like I'm moving like freely in the world. So there's a chair there in the garden here in the wall, and it's basically allowing me to go as free as possible. Uh, where I want to go because it's magnetic, and that's what I'm saying. It's a principle I'm trying to do. I used to address the kind of instability too. So this is the kernel, it's a runtime system. Thank you for watching this video. Let me upload it to the YouTube channel. Kernel looks quite nice too. So that's what I'm saying. It's already done. So basically, this is a good garden, but better garden than better garden, flowers and stuff like that. So you get a system here that respects kind of a magnetic principles of a system. So let me say, see, the title was, so basically now, see the system update, I didn't touch it, I was moving, but I was moving because the system was moving. So I'm right now in, not in the ground leaf, but I'm on the ground. So basically there's a assembly point there, guys, look, assembly point there, I didn't capture. Assembly point, that was simple there. I'm tired of it. So let me just go and show you how it works. So there's assembly point here. Okay, so it's not a bad thing, but it's a good thing. So, peace out, guys. Let me see this magnetic system and do system. So, do my work. So, basically, the system was magnetic, and that's what I'm saying. The executable was magnetic. The system respects the magnetic principles, and that's why it was able to operate the way it did. It wasn't just an electricity compiler system, it was a magnetic runtime system. And that's what I'm saying. It's magnetic for runtime execution. And doesn't matter what you run the code or not, compile the code first. If you have something that's execute and you take a tripolarity of the system and do the kind of system state, you can understand that it's magnetic principles of that it's aligned with. Thank you for watching this video.